Hello students, welcome back. Let's go to section 2 of this notebook, Constant Coefficient Linear Systems 2. Apparently, this is a continuation from section 2, and we're going to concentrate upon the application of Fulmer's method. I'm talking about these examples in particular. 3 by 3, and here's another one, 3 by 3. 2D examples. Yes, we can use Fulmer's method if we want to, but we can use the traditional Laplace inversion method and it works just fine. So I didn't really go through the Fulmer's method here previously. This time we have to. Maybe not have to, but it's going to save us a lot of time if we avoid the matrix inversion. Okay, here we go. Let's begin with a brief reminder. Let's begin with a non-homogeneous first-order linear system like this. Oh, one more thing to emphasize, constant coefficient matrix. How do you deal with this system? We use the method of integrating factor like this. Multiply the integrating factor to each entry here, and we get this kind of equation like this. And then we can apply the product rule backward to simplify the left-hand side into a single derivative, and then we integrate both sides. By the fundamental theorem of calculus, that is, integral and the derivative cancel each other out, plug in the top t, plug in the bottom t0, subtract one from the other, and that's what we have here. We're looking for y, so flip this one to the other side. That's going to give me the first equation here. And then divide away by this exponential, and here we go, dividing away by multiplying the inverse matrix. Now, matrix A and negative A commute, so we can use the exponent rule for matrices, so we can have further simplification like this. And that is the computational formula that we are going to be using. I wanted to save time, so I made it into a formula like this. And then this is something we are going to work on. All right, here we go. In this particular case, t0 is 0. So this is going to be 0. So I don't really have to worry about a t minus t0, at least for the homogeneous part. Just a times t will be sufficient because subtracting 0 doesn't make any difference here. Okay, let's begin. Let's find the matrix exponential. How do we get it? First, let's set up the resolvent matrix, or actually not the resolvent matrix, the determinant for that. So just a characteristic polynomial. Here we go, Si minus A, that's an easy computation. And then take the determinant. Here's the determinant computation. Simplify further. And then simplify even further. Please note that factor s plus 1 is common, so I can take it out. And the rest is quadratic, so this factorization is not too bad. By the way, when you have to do some 3 by 3 matrices or higher, usually it's not a good idea to expand completely and try to factorize it back. So when you simplify, please identify the common factor first and factor it first, and then what's left is going to be a little bit lower order, so the factorization is a bit easier that way. Completely destroy everything, and then you get a cubic polynomial, and then try to factor it back. That's usually a bad idea. Possible, but that's difficult. It's easier this way. Identify common factor first, s plus 1, get it out, and then what's left is quadratic, and quadratic is easier. In any case, this is what we get. S equal to 0, s equal to negative 1, s equal to negative 3, and we have these three. So s equal to 0, so we have 1, so 1 times m1, and then e to the negative t power times m2, and then e to the negative 3t times m3, like this. Okay, I switched the order of multiplication, but that's okay because this is multiplying a scalar function. I cannot switch the order of multiplication for matrix multiplication, but for scalar, yes, I can. And of course, the reason I switched the order is because of this 1. I wanted to have this 1 on the left-hand side, not on the right-hand side. That's why I did it. Okay, now that I got all those matrices, let's determine those. How do we do that? Plug in t equal to 0, that's equation 1. Take the derivative and then plug in t equal to 0, second equation. Take another derivative and plug in t equal to 0. We need 3 equations, so that's going to be sufficient. And there you go. Original, first derivative, and second derivative. Just chain rule. Oh, one more thing. M1 is just disappearing because I don't have anything here, just constant. Okay, plug in t equal to 0. Now we have this, but then again, our trouble is actually just beginning. How do I solve it? Oh yes, it is possible, but it's a tedious job. Solving a system of linear equations with all those symbols. Possible, but tedious. Elementary, but tedious. This is what I have, but... Oh, wait a minute. I think I meant M3 here. Yeah, I'm sure that was a mistake. Yes, okay, that was M3, not M1. Okay. Okay, I corrected it. So we can calculate these. M1 is 1/3 of a squared plus 4a plus 3i, like this. And M2 is 1/2 of negative a squared minus 3a. M3 is 1/6 of a squared plus a. In any case, we did all these computations. Tedious, but these are just completely algorithmic, so computers can handle it without too much trouble. I had a lot of trouble typesetting all these, actually. The computation was not. Finally, we have the desired matrix exponential because we identified M1, M2, and M3. So what we have in the end, this is what we get in the end. Okay, now that we found out the matrix exponential, let us use it. Let us use it for our purpose. Our purpose I mean by right here. We have to use matrix exponential here and also there. And for this one, we can use the matrix exponential directly because we are beginning from t0 equals to 0, so I don't really have to worry about t minus something. But here I have to do something about t minus u. Let's come back to this. And this is my matrix exponential. We just calculated through Fulmer's method. All right, let's go ahead to the solution. Okay, the homogeneous equation. And we have matrix exponential times y0. And the matrix exponential we just calculated before. This times 2, 1, 1, and it is nothing more than some elementary computation. Tedious but elementary. Am I being too quick? Of course, I'm not doing any of these computations here. I already did all those using computer and then typeset everything. I'm just following through. If you want to check all your computations, then just stop this playback and do some computation on your own. And yeah, that's going to take a lot of time because this is a tedious computation, but here we go anyway. So, we got the solution of the homogeneous equation, or blue solution, this part. Okay, next, the particular part. Okay, all right. We have to get this exponential done. And we previously found out the matrix exponential e to the at. So we have to replace t by t minus u. And that's what this is all about. See, please note that we have t minus u everywhere. And that's because I did this change of variable here. We have t minus u there. And then f of u, so these are f of u's there. We need f of u, and f of t is this one. So I've changed those in terms of u, so there we go. And then we do some matrix multiplication, tedious but elementary. And then some further simplification here. A common mistake is putting t's there, do not changing into u's. And then once you go ahead like that, it's very, very difficult to find out, because here we have both t and u, and which is correct t, which is wrong t, it's really hard to tell. Better not to make mistake from the first place, so be careful here. Once you get this, it's not too bad. We got the integrand here, so we have to take the integral and go ahead and take the integral. And then we get the red solution, the particular solution. Okay, we have everything, so add them all up. And finally, we have the solution. Add them together, homogeneous, particular, and then here is the grand solution here. This is a unique solution that you're looking for that particular initial value problem given by this initial condition here. Okay, we have enough time for the next problem here. Okay, we have this 3 by 3 matrix, and then let's find out the matrix exponential. How does it work? So let's set up the characteristic polynomial and then factor it. And we have it here, characteristic polynomial. Si minus a is an easy computation. And then taking the determinant of the 3 by 3 matrix. And oh, okay, I did not bother doing that. I left it as an exercise problem. But if you do it right, you're going to get this. E to the 2t power, e to the t power, and t e to the t power. So it looks like I'm going to get, let's see, actually I have it here. The eigenvalues are 2, 1, 1. So if you take this determinant and factor it, then I'm going to get s minus 2 for this eigenvalue, which will give me this. And then s minus 1 square, the double root for this 1, 1. So e to the t power and t to the t power for the double root. The detail is left to the students. And consequently, we get these coefficient matrices to work on. And how do you solve it? Well, I didn't really do anything. I'm going to ask you to do it. Take the derivative, second derivative, and then plug in 0. So we have these 3 equations, and with these 3 equations and 3 unknowns, m1, m2, m3, use some typical elementary algebraic methods to find out m1, m2, and m3 in terms of I, a, and a squared. Once you do that, then you're going to get the appropriate matrix exponential. And do I have the answer for that? Yeah, I do have answer here, but entire process is missing, and that's your job to fill out. Okay, all right. Now using this, you can answer the next problem. You have to do this and that. And again, I'm beginning from 0, 0, 0. Oh, actually, not even that. Initial condition y star is 0, 0, 0. So this is 0. So the blue part is going to be completely 0. So you don't really have to worry about that part at all, it appears. Let's see, the homogeneous part is going to be just all 0. And maybe I should have held back that information. In my notebook, I just left it as question marks. Obviously, I wanted you to think about, and I just ended up giving you the answer. Sorry about that. How about the particular solution part? And we have to work something out. And then we know the matrix exponential, e to the at power. So How do we get this one? E to the a t minus u, and that's for you to find out. This time I'm not giving away anything. And then f of t is like this, so f of u, and this is common mistake, by the way. And once you have the integrand by matrix multiplication, then you have 3 integrals to calculate because we have those 3 components. Good luck. Once you do all those and integrate, you're going to get the appropriate answer, and here's the answer. If you do it right, you're going to get this. Finally, putting everything together, you're going to get something. Okay, alright, I'll stop here. I left a lot of holes here intentionally, and that's much for you to fill out.